We're given a system of three equations involving x, y, z, and a parameter k. K is a positive constant. So we can write this as a matrix equation. And it's just going to be our coefficients. We've got k3 minus 1, because when we multiply this matrix, it would be k times x plus 3y minus z. Actually, this bit's not that important right now, but it would equal 3 minus k and k. Then we'll get a 3 here, minus 1 here, 1 here, minus 16, minus k, and minus k. So we're told that there's no unique solution to all three equations. We're asked to show that k is equal to 2. What this means is that there's not going to be an inverse, and the only way there cannot be an inverse is if the determinant is equal to 0. So let me call this thing, define it as a. This implies that determinant of a is going to equal 0. So let's work it out. I'm going to expand along, there doesn't seem to be an advantage of doing anything else. So I'm going to expand along the first row. So I'll get k times by the determinant of what happens if I cross this row and column out, minus 1, 1, minus k, minus k. And then for the next expansion, I'll have to do a minus, because you do plus, minus, plus. It's minus 1 to the power of an even power, then an odd power, then an even power, when I'm doing the row plus the column. So I'll get minus 3. It's going to be 3, 1, minus 16, minus k. And then plus minus 1, so that stays as minus 1. And I'm left with 3 minus 1 minus 16 minus k. Let's expand this out. I'm going to get k minus k, so that's k plus k, minus 3 lots of minus 3k minus 16, so plus 16, minus 3k minus 16. Be really careful with all the negatives here. This is going to give me k times 2k, so 2k squared, then plus 9k minus 48 plus 3k plus 16. This gives 2k squared plus 12k minus 32. Factorize out the 2. Remember, I'm setting this equal to 0 in a minute. So that's going to mean that I can ignore the 2. I can divide by the 2. I can factorize the rest. K plus 8, k minus 2 is equal to 0. So k is going to equal minus 8 or 2. Now remember, we're told at the start that k is a positive constant. That's the only reason I'm rejecting this one. And therefore k is equal to 2. We're then asked to use k equals 2 and determine whether the three equations are consistent, justifying our answer. That is there going to be a solution at all, even if it's not unique, or is there not going to be a solution? And before we look at this, here's a situation. By the way, both these are all planes. So a situation where you wouldn't get a solution would be if you had, say, a horizontal plane going in and out of the page, and then a plane going up and plane going like that, because there's no place where they all intersect. So that would be an example of an inconsistent system. Whereas you might get something like this. They all kind of intersect in one place, but you get sort of a line going through. You could also, in theory, get all the three planes, or you could get the three planes like this. Okay, so they're kind of going in the same direction, but different z value. Again, that would be inconsistent. So I'll put little crosses by these and tick by that one. You could maybe get two planes on top of one another and then a plane going through. That would also be a consistent system, in fact. But you'd be able to spot there that one of the equations is a multiple of another one. And the same if you had, say, three planes all on top of one another. And similar with this one, to be fair, you just get a different number here. But anyway, let's just have a go at putting k in. It's good to be like aware of what we're looking for, and then we'll see what happens. Then we'll have to interpret it. Okay. So I'm putting k equals 2 in. This gives 2x plus 3y minus z equals 3. 3x minus y plus z equals minus 2. Minus 16x minus 2y minus 2z equals 2. And let's call these equations 1, 2, and 3. So we're going to go through the process of solving and just see if there's a contradiction or if actually we get possible solutions. We know that they can't be unique, but it could be that actually you get like an infinite number. So the first thing I'm going to do, because I've got z and z nicely lined up here, is I'm going to add 1 and 2 together. 5x plus 2y equals 1. Then I need to combine another 2. So I'm going to go with well, not the second and the third yet. I'm going to times the second one by 3. Sorry, not by 3, by 2. So that'll give me 6x minus 2y plus 2z equals minus 4. And let me call this one equation 4. And don't forget, we've also got number 3, which I'm just going to write below. So that's why I times through by 2, because now I've got the z coefficients the same, just opposite signs. So again, let's add them together. This gives minus 10x minus 4y equals minus 2. And if I divide through by minus 2, I get 5x plus 2y equals 1. I get the same equation I had before. And what this means is that because they're multiple of one another, or they're the same thing, because I've combined 1 and 2, and I've combined 2 and 3, and we've got the same equation, that means that there's an infinite number of solutions, essentially, that satisfy. I just need them to satisfy 5x plus 2y equals 1. I can't get a unique solution. So because these are the same equation, then there will be an infinite number of solutions. The equations are consistent. And finally, we're asked to interpret the answer geometrically. Remember, they weren't like sort of multiples of one another, so we can rule out, for example, this one, or just all the planes lying on top of one another. They're all different, and so it's going to be this one, which is known as a sheaf. Okay, well done.